next board and look at L1X. Okay, people are quiet. Let me move on to the next board. So now we find L1X. So L1X will be given by X minus X naught. And then I'll evaluate this at X1. It will be X naught minus, X1 minus X naught. And this will just be equal to X minus X naught in this case is just equal to 2 over 5 minus 2. Now X1 minus X naught. If I evaluate this, I'm able to see that 5 minus 2 is just equal to 1 over 3. So I'm going to have 1 over 3 X minus 2. So therefore, the linear Lagrange interpolating polynomial Px will just be given by L naught is negative 1 over 3 X minus 5, then times F over X naught, which is just equal to F of 2, then plus 1 over 3 X minus 2 times F over 5. Right? If I simplify this, it will just give me negative 1 over 3 X minus 5, then this times 4, then plus 1 over 3 times X minus 2, this times 1. And if we simplify this, it will just give us minus X plus 6. Okay? And from here, we are able to see that actually the polynomial is of degree 1, right? So this is very easy to see. Now, if you look at the notes that I've given you, I've asked you two important questions. The first question is, what happens when you swap those points? What I mean is, in our case here, let me take you to the previous board. In our case here, we are taking this to be X naught, Y naught. And this point, we are taking it to be equal to X1, Y1. Okay, now what happens when I swap them? Okay, that is here I get, I take 2, 4 to be X1, Y1. And then this side, I get this to be X naught, Y naught. What happens? Does that affect the interpolating polynomial that I'll be able to get? Anyone who would like to answer that question? What do you think? Will that affect the interpolating polynomial, or will I get a different interpolating polynomial? Hello?
I think I can try.
You can try something.
Yes, I think since it's a linear, we are dealing with a linear polynomial, it won't be different, it will be the same one.
Yeah,
yes.
Very true, very true. So this won't affect the linear interpolating polynomial that we're going to get. It will be the same. Okay. Now, what about the second question? It says, what do the values P of X naught and P of X1 show? In other words, when I look at the linear interpolating polynomial, this linear interpolating polynomial Px, and then I evaluate it at X naught and X1, what values am I going to get? Hello, what do you think? I have P of X given by L1. If I want, I can even substitute the value of L1 there, which is X minus, the value of L0 or L0. This will be X minus X1 over X naught minus X1. And then this times F of X0, then plus X minus X naught over X1 minus X naught times F over X1. What happens when I evaluate this P at X naught? What value will I get?
We are getting the original one, which is 4.
Okay, so we are getting f of x0.
Yes.
Similarly, when I evaluate f of x1, I'm also getting f of x1. Okay, so this is what we expect when we are talking about polynomial interpolation. We should expect the polynomial p that we're going to find to give us the values of f at those particular points. So if this situation happens, we say that this polynomial p is interpolating the data, the given data. Okay, we say that it is interpolating the given data. Okay, so at those particular points, we should be able to get the given values f of x naught, f of x1, and so on, right? So that's what we'll be able to see. Yes, Mr. Mwape?
Yes, sir. From what we are learning today, like under this this method, so far we have learned that what we are finding the p of x is actually approximating the original function f of x, which we don't know in this case. So can we have a situation whereby after we find p of x and we try to evaluate p of x naught, in this case it gave us what we expected. Now, is there a situation whereby we don't get the exact values? Let's say maybe we got maybe 3.9 or a value which is very close because p of x is just approximating the original function. So can we have that scenario?
No, I would say no, because we want this px to interpolate the given data.
Okay.
Okay, so at those given points, I need to have f over p of xi to be equal to f of xi. You see that that's the same concept we are going to carry on, even when we look at quadratic and higher order polynomials. Yeah, but of course, in this course, we're just going to look at the linear, quadratic, and cubic polynomials, but you'll be able to see that it is important that it should be able to interpolate those values. But for example, if I have 2 comma something, let me just say for 2 comma f of 2, and I also have 3 comma f of 3. Those values f of 2 and f of 3 should also satisfy p of 2 and p of 3. But I can try to use that px now to approximate, for example, f of 2.1, for example. I'll see that this 2.1 now is between 2 and 3. So I can pick values in between there and try to approximate those. But what I want is that this polynomial p should satisfy the function at those given points. Is that okay, sir?
Yes, it's very clear.
Okay, and then, okay, Mr. Simmons, you can just ask your question. I don't think I'll be managing to go to the chat section and then read your message. I think it would distract me somehow. So just unmute your mic and then you ask the question that you have. Okay, so let's move on and try to generalize the Lagrange interpolating polynomial. Now, before we move on to that, there's something we need to note. We see that when we have 2 points, like in the example, we were given 2 points, and in this case, we're able to find the polynomial of degree 1. right? It will give us a linear interpolating polynomial. So that means if I have 3 points, or if I'm given 3 points, then you'll be able to find a polynomial of degree 2. Okay, and I'll move on like that. So if I have n plus 1 points, then this will give me the n or the polynomial of degree n. So just say in this case the degree will be equal to n, right? So in this case, for example, I can have x naught comma y1 or f of x naught. Then the other point I can have is x1 comma y1 and so on up to xn comma yn. Then using these points, I can find the interpolating polynomial of degree n. That's what I'll be able to get. Okay. And then when we construct the nth interpolating polynomial, then we first need to construct. So we need to construct lnkx for these values of k from 0 up to n, and it should have the following property. So with the property, this property is lnkxi should be equal to 1 if I is equal to k, and it should be equal to 0 if I is not equal to k. Right? So you should be able to construct that lnk. The n there is just indicating the degree of this polynomial that we're going to get. And then k will just depend on those points that you are given. For example, if you are given 2 points, then you should find you should find the value of ln0 and ln1, right? So if I have 5 points, then I should find 5 different expressions for lnk for those different values of k. Now, this property is saying if this k is equal to the I that you have there, then that value of lnk at xi should be equal to 1. If they are different, then it should be equal to 0. Okay. This is something that we are able to see from the example that we looked at. So let me just move on to the next board, and then we are going to illustrate it using the previous example. So from the first example we considered, example 4.1.1, we found L, if I want, I can even say L10. So the 1 there is just denoting the degree of the polynomial that I'm going to get. Yeah. Now in situations where we understand that actually the polynomial we are looking at is the nth polynomial, then we can just write it as, we can just omit it if you want. Okay. Now, for the sake of that notation, let me include it. So we found L10 to be equal to negative 1/3, then x minus 5. This is the expression we got. And for I'm starting, yes. Okay, now I'll move on to the next value for L11x. In the previous example, we just denoted this by L1. Yeah, but now we need to indicate the degree of this polynomial that we are looking at. So that's the reason why I'm putting that one there. So we found this to be just equal to 1/3, then x minus 2. Okay, so now using these two, let us try to evaluate L10 over x0, and also try to find L10 over x1. Okay, So according to this property that we have here, it shows that if I is equal to k, then we should just get 1. If I is not equal to k, then we should be able to get 0. Let us see if this property is satisfied in this case. So we are able to see that in this case, we are getting L10 over x naught is just equal to, yes, Mr. Shilengwe.
Yes,
Can see
a bit confused. Yeah. What is the value of k exactly?
Okay.
Where is it coming from?
Okay. So let me take you back to the linear interpolating polynomial. Where is that board? Yes, it's here, right? So the k are these values we are getting here, 0, 1, and so on. If I was looking at the interpolating polynomial of degree 2, then I'm also going to get L something 2 here, right? If I've been given 3 points, that's what I mean. Is that okay?
Yeah, that's fine.
Yes.
That's okay.
And then, yes, and then the n, like I mentioned earlier on, this n here, let me show you the other board. Which board is that? Okay, it's this board. This n, like I mentioned here, is the degree over the polynomial that you're looking at. So if you're looking at 2 points, then you expect k to go up to 1 there, okay, because you are going to have x naught and x1. Okay, so the n in this case will just be equal to 1. So you just go up to 1. If you are given 3 points, you go up to 2, and so on. Now I mentioned that if you understand from the